Hi everybody, my name is Max Maker and in this video I'm sharing with you how I installed a heat pump in my new workshop. So the building was up in about August and I could start working on the interior. It's about 600 square meters on the inside, has a nice roof overhang, the walls are 6 meters high, so it's a really big building and it was all empty inside. So the first thing that I installed was the heat pump to get ready for the winter. When we poured the concrete slab, we buried water pipes to heat up the building later. And where the ends were sticking out, they needed some fixing. There was pressure on the system for 3 months, so I could be sure there were no leaks, and now I could release that air. When we poured the concrete, we didn't have anywhere to fix this to, so now it's crooked. But it's okay, I'm just going to take it off, take all of these connections off, cut them to the right size, and then install it straight. But first I went to the hardware store to get these sawhorses. These are ready-made, they cost 15 euros and they're super sturdy. I like them a lot because I don't enjoy working on the floor at all. So now it was time to take all of this off and to install this cover. This is a steel cover, it makes everything look nice and keeps the dust away from the valves. But I had to make some adjustments to it because the pipes at the back were sticking out a little bit too far. Normally in Germany you fix this manifold to the wall that's already standing and then you pour a second layer of concrete. But we did it the other way around and that's why everything is a little bit crooked. On this manifold, everything is quite spaced out, so I had to make some cutouts in the back, especially here. But this is okay now. We're a little bit further away from the wall, but I think that is fine. I mean, it's a giant workshop. What doesn't matter if this one is a little bit further forward. And then I fixed these covers to the wall with these brackets, and for that I'm using rivets. The wall is made from the sandwich panel, so it's steel on both sides and some foam in the middle. So it's basically sheet metal that you're working with, and rivets are perfect for that. They're super easy to use, very quick and very sturdy. And then it was a matter of fixing this manifold in place very nicely and to align it properly. So these two manifolds are straight now, and here are the pieces that I had to cut off. So this is literally the height difference that we had. And we couldn't have worked to any better tolerances because this thing wasn't fixed to anything. I mean, we haven't had poured the concrete at that point, so there was nothing to fix this to. But I think for that reason, we did a pretty good job with only this kind of height difference. But on the third manifold, 2 of the pipes were too short, but I fixed that by using a press coupling, which is naturally a little bit longer. First, I need to calibrate the ends, so that makes it round again and gives it a round over. And then you just put the push fitting over there, or the press fitting. And then you press it. And for that I used the Rems Mini Press 22V. Rems is a German manufacturer and they were so kind to provide this high quality tool for this project. And knowing what I know now, I should have done all of these with press fittings instead of screwing them on like you see on the left and the right side. So after these were fitted again, I could pressurize the system to make sure there are no leaks, and there weren't any, so that made me very, very happy. Next I had to connect all these manifolds to the main buffer tank, and luckily my parents just happened to have a stainless steel one left over at their house. By the way, this is the garage where everything started. There's just one problem with it. We have one inlet at the bottom, one down here, and one outlet at the top, and everything else is underneath, so I need to change that. So this is a heat exchanger, so we have some coils in there and I need to remove them because we don't need a heat exchanger anymore, because the warm water from the heat pump will go in there and the warm water will come out and go into the concrete. So this is a different kind of system where the heat pump sends hot gases into the water and that heats up the water. But I don't need all of this and I can just replace it with a system that works for my setup. And the inside of the tank is still looking brand new. Because it's stainless steel, it doesn't corrode at all. So I had this new bottom plate laser cut with exactly the right dimensions that I need for my setup, and then I could build this custom gasket for it. And cutting this stuff is very easy. You can just drill it or use a box cutter. You buy this as a sheet and then you can customize it to your needs. So with my heat pump, I want as much water to flow through here as possible. So I chose the biggest pipes that I could fit in here. And since I'm doing this myself, the cost of these fittings doesn't really matter at all. I save so much money instead of hiring a professional company to do this, that you can opt for the biggest pipes, and with bigger pipes you never have any drawbacks except for the physical size. It's always better to have bigger pipes than too narrow pipes. Underneath the tank cover I had to make some connections to the manifold of the radiant floor heating system. And for that I had to install some brass elbows. And first you have to roughen up these threads a little bit so the hemp can stick in there, otherwise the hemp rotates with the fitting when you screw it on. Then you wrap some hemp around, add some lubricant that makes it easier to twist the fittings and also keeps the hemp from drying out. And the cool thing about this hemp is that it swells up when it gets wet and it can seal off some minor leaks. And then I color coded the elbows to make sure I don't mix up the supply and the return lines, because the supply with warm water has to go to the very top of the tank. So on the inside of the tank I attached some hoses to here, so they deliver the water to the top of the tank, and at the bottom you can suck out all of the cold water. You don't want them to mix up. But then I noticed that these service ports are too small to reach the connections comfortably, so I elongated them so they stick out from the bottom and then you can reach them. But that meant that I had to elevate the whole tank, and for that I found these things. These are used for deck constructions, as you can put a wooden beam on one side and you can drill the other side to the concrete floor. And the cool thing is they are super sturdy and they're height adjustable, so I can nicely adjust it so the tank is standing upright. All I had to do was to drill a hole in the middle and then tap it, and that way I have some nice threads that connect to the rubber feet that were on the tank already. So that way it's easy to adjust everything and to mount it to the floor. So now the tank was in place, but before connecting everything I had to set up the outdoor unit, because that also had some inlets and outlets that go inside of the building, and I had to know where they would come out of the wall. To find the right size for the heat pump, I did some heat loss calculations for the workshop. The heater needs to supply as much energy as you lose to the outside. The calculations were very easy for this building because the walls are all made from the same material. If you have an existing building, you can also check the size of your current heater, but be aware that gas heating systems are often oversized. Alternatively, you can also hire an engineer to do the calculations for you. For me, they came out to be about 36 kilowatts when it's minus 11 degrees outside. Why minus 11? That's the norm outside temperature for my postcode, and you can look that up online. It's the coldest temperature that happens 10 times in 20 years. But I think it's a very misleading value for well-insulated buildings. It only shows the absolute minimum temperature, and those are extreme outliers. In the past 5 years, we reached it only in 2 nights. If you have a well-insulated building, even if the heating is off, the temperature inside will barely drop in those few hours. If you do the calculations for about 0 degrees, it comes out to be about 20 kilowatts. And 20 kilowatts was often the biggest model that any manufacturer had in their product range, so it was an easy pick. Otherwise, I would have had to buy 2 heat pumps, and keep in mind the second one would only run 2 days in a year. So now you know how I selected the size of the unit, let's install it. So I went to the hardware store and bought some of these shelves to build a concrete form out of it. And the cool thing about these shelves is that you can get them in all kinds of sizes, and I have to do minimal cutting in the workshop. And they're also small enough that they are easy to carry and to transport in a normal car. Otherwise, if I buy a whole sheet of plywood, it's difficult even to carry it. And the cool thing is they're also waterproof and they're very smooth, so you get a nice finish on the concrete. On the inside, I add a little bit of caulk and smooth that out, and that way we get a nice chamfer on the outside of the concrete. Now some people ask me what this workshop will be for. I'm a product design engineer and I do a lot of prototyping, so most of my time is divided between computer work and time in the workshop. I also manufacture some specialty items for the caravanning industry, so the workshop will be mixed use. I cannot see myself ever stopping to make stuff, so this is hopefully a good investment for the future. I noticed that I needed a way to vibrate the concrete, so I thought, maybe I could build a concrete vibrator. Because I don't really do a lot of concrete work and I never bothered to buy one of those, and they're also quite bulky, so storing them is difficult. Some other specialty tools that are small, I can just throw them in a drawer and keep them for years, but the concrete vibrator is just huge and I don't want to have one around. So I thought maybe I build my own by using this leftover pipe and just some threaded rod. And that looked very promising. This took me about half an hour to make. So the next day, my crew and I, we went to the workshop and we set up the forms, and they are resting on crushed concrete, so it's a good basis where they cannot sink down into the ground. I mean, this is not water soluble. We made sure everything is level and plumb, and then we added some more bracing to the outside surfaces so they don't bow out, because that would look really stupid, especially after all this work with the forms. So now it was ready for pouring, and first we watered everything. That's always a good idea, to give everything enough moisture to cure. And then we filled it up with concrete bags and mixed it right inside of these forms. And this is not the optimal way to do it if you want really strong concrete, but for these foundations it doesn't matter very much. The whole unit just weighs 200 kilograms, so that's about 2 persons standing on it. So I think we will be fine. If you want really strong concrete, you definitely should follow the instructions on the back. So 2 weeks later I took the forms off and the concrete still looks a little bit uneven, but that's just because it was wet. It's still drying, and once it's dry it will have a uniform color. And we had some sharp edges at the top, and I knocked them off with an angle grinder and a concrete disc. Now the outer unit will form a lot of condensate and that will drop down onto the concrete. So to protect the top surface I added some tar paper. To move this unit we have to take the lid off, so I removed these screws, and underneath here should be some points where we can attach some straps. What we have in here is down there is a compressor. That's the same thing as you have in the fridge, and that makes warm or cold cooling fluid inside of these pipes, and this cooling fluid is then the temperature difference is going to be transferred to the water, and the water is what gets pumped inside by the indoor unit. This is just a really big fridge, and here on the back you can see all the fins where the heat is exchanged with the outside heat. And in the summer this thing can also cool just like an air conditioner, and we have this massive fan that pushes the air around. And now I want to lift it, so I'm going to attach some of these straps here. Luckily the rebar people left these straps behind. I think they were supposed to collect these, but they didn't, and now I'm going to borrow some. Sorry about that. So this outside unit contains a closed circuit filled with propane gas. And that propane gas gets circled between a compressed state and an uncompressed state. And in a compressed state it's warm, as any gas warms up when it's compressed, and that warmth can be transferred to the water, and the water is sent inside of the building. And when the gas gets uncompressed it becomes cold again. So cold that the ambient air outside of the building can warm it up just a little bit. And once you compress that again you created some more energy that you can turn into the water. You don't really create energy, you just pump it from one place to the other. That's why it's called a heat pump. And it's exactly the same as an air conditioning or a fridge, but the cool thing is it has an efficiency of greater than 1. So you take 1 kilowatt of electric power and it turns that into 3 to 5 kilowatts of heating power. So it's a very efficient way to heat this workshop, especially combined with the radiant floor heating, because heat pumps are good at low supply temperatures. So at 30 degrees it's very efficient, and 30 degrees should be enough to heat up the whole workshop. And the best thing is that this also works as an air conditioner, so you can reverse the process and in summer you can cool down the workshop. And just after I was done tightening this down, it started to rain, and when I came back outside I was really shocked. The foundation nearly completely washed out. There was a downspout next to this, and all of the water was coming here instead of going into the pipes because it wasn't connected yet. So I quickly ran to the hardware store and bought 30 bags of gravel to fill up this cavity. And I meant to fill up this cavity anyway, but just later and in my time. This is for the condensate water to have a place to go somewhere. That was a bit stressful, I have to say, but at least now it's done. And otherwise, if I had spent my time, I would probably have spent half a day doing just that. And now I did all of this in maybe 45 minutes. So one less task that I have to do. And over here, I dug a new hole for the weekend, so the water from here can go in there, and I built a little dam. I think this will be all right. There's so much gravel in there now that the concrete cannot slip down. A few days later I covered the gravel pit with some leftover foam insulation to protect it from the frost, and then I covered it up with dirt. So the outdoor unit is somewhere behind this wall, and we have to drill some holes to get the water inside of the building, and from here it will go into the tank. In the tank it will collect, and it will be sent to these 2 manifolds and to this one as well. And we also have the indoor unit with all the electronics inside, and that will be installed here right now. This is the bracket for the indoor unit, and I'm going to install it on these brackets because I can screw these to the beam up there. So why did I choose this specific model? I read through the manuals of 8 different manufacturers, and at the end of the day this one had the best. It seemed very well thought out, and given that they don't make any money with the manual, it was a good sign that they put some effort into it. But I don't know if this one is any good. The technical values for all the pumps from all the manufacturers are very comparable. And it will come down to how well the support works if this thing breaks down, because there's nothing I can do about this. I dealt with some companies in the past that offered no support whatsoever once their product was sold. So nowadays I like to call the support hotlines before I buy something
to see if they have any pride in their work.
So this is the indoor unit. The water flows in here. Through this pump, it gets circulated into the buffer tank. And from there, we have another pump that circulates it around the building. So we have two separate pumps. This is a electric heater. This is an additional heater. So if the heat pump cannot produce enough heat, we have another 9 kilowatts of power here. So it will heat electrically. And that will only happen if it's really, really cold outside, like minus 10 degrees, I hope. We'll see how it goes. And from here, it can then be diverted to one of these two outlets. So one is for the buffer tank and the other one is for hot water for showering and stuff like that. But we're not using that because the hot water for the showers will be by an electric heater. So a completely separate system, because I don't think we'll shower that much over here. It's not like a family home where you shower every day. It will only happen occasionally. And in those cases, we can just use the solar power. And over here, we have all the electrical connections. So some of these are just for power, just for something like this pump over here, just regular power. And here we have three-phase power, and this goes via these relays into the extra heater. So this is getting two power sources. And we also have some bus connections that go from here to the outdoor unit that's currently indoors.
Supplied together with the indoor unit came 3 of these strange looking copper pipes with the O-ring. The O-ring goes into the indoor unit and the bottom you're supposed to solder to your water connections, but I didn't feel confident soldering this. So instead I used these compression fittings and they work by tightening, and that way this little olive in the middle, is called an olive, gets pushed into the copper and that makes a waterproof connection. You just have to cinch them down, but not too much and not too little. And you need to use the lubricant. So now instead of the blank copper, I had a nice thread, and I can use that thread to screw other stuff to, like this press fitting. And this press fitting is for 50mm multi-layered composite pipes, and that's the stuff that I'm using to connect all the manifolds together.
Turns out these are super easy. I thought I have to push them in from here because that's the way you have to do it on my pressure washer, but you just put them in from the outside. That's it. Really strange that this is waterproof, but the rest of the stuff is really beefy and heavy. But here it's just these little clips and an O-ring that holds everything together.
But before I laid any pipe, I had to know where the inlets from the outer unit are going through the wall, and I used a laser for that. And I marked a hole 3 centimeters above the laser, so the pipe that will connect the inside and the outdoor unit will have a slope going outwards, so any of the rainwater doesn't have a tendency to flow inwards. And I had to know where the pipes come in to leave some space for later to connect everything. A few days earlier, I bought a ton of couplings and this shelf with boxes to sort all of them. I have some T's, some with threaded connections, because of a lot of components in plumbing still have threaded connections, and of course also some elbows. And all of these connections cost between 15 and 25 euros depending on the complexity, and these are all in 50mm diameter. In total, I spent maybe 1.5 grand just on the couplings, but overall that's super cheap for this kind of heating system. By doing it myself, the size and the quality of these fittings really doesn't matter because they're so cheap compared to all of the money I would have spent on labor instead. So the decision to go with the biggest couplings possible was made very easy because overall the cost is so little and bigger pipes are always an advantage. They mean less resistance and a higher flow rate, and the higher the flow rate, the more water we can push through the concrete, and thereby the supply temperature can be even lower, because heat pumps are very efficient at low supply temperatures. That's why sometimes if you retrofit them in old houses, you need to replace the radiators to get more water to flow through.
So the hot water comes from over here, and I could put these two together, so in parallel, even though they look like they're in series. So this one after the other one. But this one is for the office, and I want to keep this separate, so I can turn this one off and still heat the office. So that's why I'm going with the pipes behind this one and then into the tank.
So all the fittings that I'm using have an outside diameter of about 50 millimeters, but the inside diameter is always about 40 to 42 millimeters. And these fittings, of course, they are a little bit smaller, but they're also very short. They're just 10 centimeters in length. So you can go with smaller cross sections there. The pressure drop is not that much. But the pipes, of course, are very long, and there you want a big diameter. So these are composite pipes with plastic on the inside and outside and an aluminium pipe that holds everything together. And after cutting them, you need to give everything a chamfer to make some nice rounded over edges, and that way you don't destroy the O-rings that are inside of these fittings. but the fittings have a little bit of holding power, and that way nothing falls apart while you assemble everything. And of course you need a press, and Rems was so kind to send me this one. This is the Rems Mini Press 22V. It's an amazing industrial machine and it works really well. It has different attachments for the front, so different clamps. This is the 50mm TH profile. There are different profiles for different fitting manufacturers, but this is a very common one, I think. And this is super nice. It's very heavy, but it presses them with ease, and the whole system is just super. You don't have to solder anything, you don't have to work with flux and heat and all of that. And it is a very easy connection that anybody could do, even if you're not a professional. And in Germany and most of the hardware stores, you can rent them for a day for a very small price and press all your fittings. And then 2 weeks later, you can return to press the ones that you forgot. So anyway, you just cut the tubes to length, assemble everything, do a test fit, and then you press them properly, and then you can be sure to have a really good connection. So the white pipe in the back comes from the first manifold, but there wasn't enough space here to place a T. And there was also limited access here because we were so close to the back wall that I couldn't press this in place. I took everything out and did this on the sawhorse. And that way I could make sure that the elbow at the end is exactly at 90 degrees, because otherwise it's a little bit difficult to put the clamp around it and to make sure that it's pointing in the right direction, at least with the other side of the fitting not connected yet. So instead of the T, I came up with this solution, and the cool thing about that is that I could swivel it around and get the angle perfect, and all I had to do was to cut the right length for the attaching pipes, and then it was good for pressing. But before I did that, I had to fix everything in place to give it some structure, and I'm using these rails for that. They're just fitted to the wall, and here the very first one is at a 45-degree angle, and for that I printed these blocks that position it perfectly at the right angle, and that way I could start fixing the pipe to the walls. And that gives it some structure, sets everything in place, and then I could start pressing. And I did so many presses, I think about 200 in total for the whole system. If I had to do this by hand with some kind of hydraulic clamp, it would be very difficult. But with this, it was very fun and easy. But at times we also used 2 people because this 50mm clamp is very heavy, and sometimes it was difficult to see if you clamped the fitting at the right spot and if the pipe was still pushed in all the way. So the warm water will come from the buffer tank and go to the right and to the left into the manifolds and the supply side, so that's at the bottom. And at the top it returns through this pump and then back into the buffer tank. But if there's any air left in the system, the bubbles will collect at the top of the loop just above the pump, and to get rid of that air I'm installing this valve. So this lets out any of the air automatically, but it stops the water from going through. And in total I installed 6 of these, always at the highest point of all of the pipes. All of this side is done now, and we did this big bow so we can look at the display at a comfortable height. So the manifolds are connected to the buffer tank now with a supply and a return, and they have a dedicated circulation pump. The heat pump also gets connected to the buffer tank with its own set of supply and return lines. The indoor unit contains a small circulation pump to keep that water flowing. So there are 2 separate circuits and they only meet inside the buffer tank. That's why the buffer tank is also called a hydraulic separator. So the cold water is coming out here, going in here, and this is a mud filter or sediment filter. And after that, that's just a fine steel mesh, that's another filter. And then it goes outside and we can close it off here. And it comes back inside through this pipe. And here I still have to make the connections. I will insulate these pipes at some point, but not right now. It's low priority because we don't really lose energy. It just goes into the workshop where I want the heat to end up anyway. So this is a job for sometimes next year when I don't have anything else to do. On the outside, we buried 2 of these pipes and therefore the electrical connections. So one is for the power supply and the other one is for the connection between the indoor unit and the outdoor unit. And I always like to choose these very big pipes because that way it's much easier to get the cables through. If you have too small the pipes, then you just get stuck and it's frustrating. This is very easy and they don't cost that much anyway. So now I could make the final connection between the indoor unit and the outdoor unit, and I have these couplings for that, and these are flat sealing couplings. So if the outdoor unit should ever break, you can just unscrew them and take it off and you don't have to do any more press fittings. And for the pipe, I bend it a little bit, as you see there. So that's exactly the 3 centimeters of height difference that's between the holes on the left and the unit on the right. So it's sloping downwards and the water can never flow towards the building. So this heat pump has an outdoor unit and an indoor unit, but some manufacturers, they also build heat pumps where everything is built into the outdoor unit. So there's only one device that you have to install, and I think that would be easier to install actually. But maybe it also has some disadvantages for service if some of the components are on the outside where they're not heated, and here it's easier to reach all the stuff because it's on the inside. And then there are also heat pumps where you don't set warm water inside of the building, but the hot refrigerant gases. And I think there's maybe some technical advantage to that, but the big disadvantage to that is that you have to deal with refrigerant gas. And here in Germany, you cannot do that unless you have a special license for that. Otherwise, you get big fines, because if you do a mistake and you leak refrigerant, that's really bad for the environment. So in this model, the refrigerant stays inside the outer unit, and I'm only dealing with the warm water.
Job done. Heat pump installed. Now we're ready for winter. But right now it's still summer and really beautiful out.
Well, I wasn't done quite yet. There were some finishing touches like this security group. So you can just buy this off the shelf. And on the left you have a pressure gauge. In the middle there is an air vent. And on the right side that's an overpressure release valve. So this releases the water. It goes through this pipe and then outside through the hole in the concrete. And there are also two more of these, one in the outer unit and one in the indoor unit. So I think I should be safe there. And then I did some insulation because I don't want to heat the garden. And for the first layer, I'm using PE foam. This stuff is super cheap, about €5 per bar. And this is waterproof because it doesn't absorb any moisture. But this stuff is not thick enough on its own, because if you have a 50mm pipe, you need 100mm of insulation thickness. So I added some nitrile foam around of the rest. So this comes in sheets and you can wrap it around, and I had it left over anyway. And that's why I have the required thickness. And especially there on the left where I had the brass couplings, it would be difficult to choose anything else but this nitrile foam because it's so flexible and it's easy to make a connection. They also sell some pre-made pipes that are insulated and they have 2 water tubes on the inside, so that way you can bury them underground. But I just chose to go through the wall straight away because I think it's more flexible in the long run and it doesn't matter here because I have so much space anyway. So that white sheet is just a release film that was on the self-adhesive of the nitrile rubber foam. And I just wrapped it around for some additional waterproofing, and then I wrapped everything with aluminium foil. And the aluminium foil is there for the UV protection. So I think this is a nice package. It's waterproof, it's UV proof, and it's heat proof. So I think this should work out. While I was researching this whole install, a lot of people told me that I should get a professional to do it, with the justification that it wouldn't work properly. And I totally disagree. Here in Germany, for certain trades like roofing, plumbing or heating, you need to have a master in that field. But that doesn't automatically mean that you're also good at your job. I have had plenty of workers that were so-called professionals but did lousy jobs. Like this installation right here. It was done by a proper heating company, but the installation is a real mess. It was one of those cases where they only cared about posting the bill. And this installation is definitely not enough. By doing this myself, I gain a ton of experience, save about 70% of the costs, I have a lot of fun while doing it, and I know that I won't be scammed.
So I just took this bucket, poured it in there to check if there are any leaks. There was one leak, but there was just one of these nuts that was completely loose. And all these elbows right now are completely dry, so I'm pretty confident that this is all waterproof with all the hemp in there.
So I installed the heat pump in summer and I had to wait for another 3 months for the power to be turned on. That was unexpected but out of my control, so I waited for the power before I filled the system with water, otherwise I would have to worry about it freezing. So as the water was rushing in, I had to let the air escape. Some went through the red bleed valves, but most of it came through an outlet, and I attached a hose to that and stuck that into a drain. As the pressure increased, I found some more leaks. There was another nut that wasn't tight, that was an easy fix. And then there were leaks at the bleed valves. Funny enough, they came with some sort of a sealing contraption from the manufacturer, but that didn't work, so I replaced it with Teflon tape. And this device gets rid of the microbubbles inside the water stream. This assembly was leaking, and I think the issue was this nut right here. Because this nut is on the inside of the tank, which usually you shouldn't do, and I forgot to put in the second gasket. I only had this green stuff underneath this nut, which is fine, it seals the nut against the steel plate, but there was no sealant between this thread and the thread of the nut, so the water could just seep through there and come out the other side. So now I fixed this, I removed the green stuff and I replaced it with rubber, because the rubber easier pushes inside of these threads, and I put some rubber underneath as well, so the flange side is also pressing against this. So now we have two seals instead of just one, and it's more compressible than this stuff, so I think now it should work. Removing the tank is not too hard with a forklift, but I still hope I never have to do it again. Some kind of a hook at the top would be very nice. But hey, it was for free, so I'm not complaining, and it's made from stainless steel, so it will probably last forever. With the feet, it's easy to make it stand up straight. And for the connections between the pipes and the brass, I'm using unions. You can take them off as often as you need for maintenance, and that makes it very convenient. 2 days ago, I noticed that this pipe is touching the housing over here. And I remembered when I installed this, I paid attention to make sure this is not touching and that this is going straight down, and I did that by adjusting these lengths. And I thought, maybe I did a mistake, so I thought nothing of it. I just pushed it over a little bit by loosening these two clamps, and this has a little bit of give, so I could just push it over a little bit. But today I noticed that this coupling isn't pressed. And this, if you check this side, here it is pressed, here's no gap, here's a gap. So the pressure from inside of the pipe pushed this pipe out, and that's why it's touching on one side now. So I gotta fix this. So I turned the water supply back on and checked for more leaks, and of course I found one, but this one was rather obvious and very easy to fix.
So right now all of the valves are open, and I'm just trying to fill everything up as much as I can. And after that I can close all of the valves and only open a single one, and then I can rinse that until only clear water is coming out without air bubbles. And that way I get rid of all of the air. But at the moment I'm more interested in whether everything is tight or not, or if I have any leaks.
So now I could finally turn it on. It's November and the outside air dropped to about 5 degrees C, and inside the workshop it's 11 degrees. So it was really time for heat. And with this thermal camera from Top Done, I could check if the heat pump was actually working. After about 10 minutes, the supply pipes coming from the outer unit started to get warm. Another 10 minutes later, the buffer tank was warm and started to pump warm water into the manifolds and of course into the concrete. The return lines were still cold at this point, as all the energy was transferred to the cold concrete. And after 4 hours I came back and I could see that the floor was actually warming up. Of course I wanted to know how efficient it was, and at the display it showed that it consumed about 3 kilowatts of electric power and turned that into 21 kilowatts of thermal power. That's an efficiency of 7 to 1, but that's not normal. That only happens when the building is warming up. After some time, the heat exchanger kept freezing up, but that is normal during the winter. The heat pump then just reverses the flow of water and takes some of the energy that is stored in the concrete to melt the ice. Because the building was still cold at that point, it also used its extra electric heater and produced 30 kilowatts of power. That is a feature that consumes a lot more energy and hopefully will never be necessary once the building is warm. I climbed up to the storage area, and from there I could see how the floor was heating up. The beauty of the radiant floor heating is that it can even heat if the supply temperature is just barely above room temperature. After about 3 days we reached 20.5 degrees, and that was actually too warm to work in there. I guess I earned the right now to wear this t-shirt. So now the big question is the heat pump that I chose big enough for this big workshop? And the answer is yes. We have 18.2 degrees on the inside right now, so that's a good temperature to work. And on the outside, for the past week, it was about 0 to 5 degrees, so just about freezing. And right now, only half of these valves are open, so we're not even heating with the full capacity. And the heat pump has 26 degrees of supply temperature, which is amazingly low. I thought we would have to go up to 30 or maybe 35 even. So the radiant floor heating is working really well. And right now it only uses 0.8 kilowatts of electric power to produce 7 kilowatts of heating power. That's just 15% of the total power that we have at the disposal. So the heat pump is plenty big enough, and it remains to be seen what's going to happen when the temperature drops to minus 11 degrees. But
Judging from the last 5 years, that only happened for really just 2 or 3 hours in the very morning hours. And after that, during the day, it always heated up to about 0 degrees. So yes, the heat pump is definitely big enough, even though some calculations said I would need 2 of those. So I think we're good. And these offices, they're all insulated from the workshop, so I can only choose to keep the offices warm at 23 degrees and just let this cool down if there should be a really, really cold winter. Then this will cool down maybe to just 10 degrees, but the office and the toilets and the showers, they will stay warm.
If you're interested to see how we build the rest of this workshop, please subscribe. I got a few more videos in the pipeline and I think you will enjoy them. If you have any questions or opinions, please leave them in the comments, especially about the heat pump. And thanks for watching, everybody. My name is Max Maker and I make all kinds of stuff.